Welcome to module number 1, Enterprise Architecture. Let's take a look at what we're going to be covering in this module. We've got 6 different lessons. In our first lesson, our focus is going to be enterprise network design considerations. Here we'll contrast the traditional 3-tier design, where we have an access, distribution, and core layer, with a collapsed core design. We'll contrast on-premises networks versus cloud deployments, and there will be a big focus on redundancy. Then we'll follow that up with a look at wireless LAN design considerations. What are some different ways that we might deploy a wireless LAN? We'll discuss things like location services, how client density can impact our designs, and we'll take a look at how we can logically segment our wireless networks. Then in our third lesson, we'll take a look at SD-WANs, software-defined wide area networks. We'll see theoretically how they work and take a look at some of the pieces and parts that make up Cisco's solution when it comes to SD-WANs. We'll follow that up in our next lesson with software-defined access, or SD access. Here, instead of having a bunch of access control lists, for example, where a user's access might be tied to their IP address, instead of doing that, we can identify our user, put them in a group, and then give that group a certain level of access, no matter where that user is physically on the network. In our next lesson, we'll consider QoS, quality of service. How do we treat some traffic better than other traffic? And then we'll wrap up this first module with a look at switching mechanisms. And here we're not just talking about Cisco Catalyst Layer 2 switching, we're talking about packet switching inside of our routers. We'll talk about Cisco Express forwarding, we'll contrast the CAM and the TCAM that we do have inside of our switches, and we'll compare the FIB, the forwarding information base, with the RIB, the routing information base. But let's get started in our next video as we contrast a 2-tier design with a 3-tier design. In this video, we want to consider a 3-tier architecture and a couple of 2-tier architectures. First, let's consider Cisco's traditional 3-tier architecture, where we have an access layer, a distribution layer, and a core layer. Down at the access layer, that's where we're connecting out to end devices like PCs and laptops and printers and wireless access points. And it's common in a building that has different floors that we've got a set of access layer switches on each floor of that building. Maybe there's a wiring closet on each floor, and all of our devices on that floor, they home back to that wiring closet and they plug in to access layer switches. But within the building, we might have those wiring closets stacked. That's a common way of doing it. And we've got riser cable running from one floor to another floor to another floor. Well, all those floors, all those switches in the access layers, they home back to a building distribution layer switch. And at the distribution layer, we're interconnecting the access layer switches. And we're also providing a pathway to get out to the rest of the world, maybe other buildings in a campus environment, maybe out to the internet. And if we do have more than one building, let's say in a campus environment, a business campus or a university campus, we could interconnect our different buildings. Specifically, we can interconnect the different building distribution layers with a core layer. The core layer's primary concern is speed. It wants to get traffic as quickly as possible from one building distribution layer switch to another building distribution layer switch that might be in a different building. And it also can get us out to the internet or maybe over the IP WAN. But that's Cisco's traditional 3-layer model. And if we take a look at the actual topologies involved here, we can see we've got a mixture. Think about it. We've got a star topology down at the access layer. We're starring out to all of those different devices. For redundancy, we're interconnecting our switches between our layers. That would be a partial mesh topology. And since we've got both a star and a partial mesh topology showing up here, we can call this a hybrid topology. It's a mixture of different topologies. But again, this is the traditional 3-tier architecture. However, sometimes we don't have enough buildings to justify having separate core and distribution layers. Maybe we only have a single building. Maybe it's a SOHO environment, a small office, home office environment. In a case like that, we can take the responsibilities of the core and distribution layers and we can consolidate them into a collapsed core architecture. With a collapsed core, we combine the functions of the core and distribution layer switches. Specifically, this collapsed core, it can connect out to our access layer switches, And it can also get us out to the internet, and it can interconnect our different access layer switches. That's a collapsed core or a two-tier design. Another two-tier design I would want you to know about is often seen in data centers. It's a spine leaf design. And here we've got switches maybe within a rack, and those switches might be connecting to servers in that rack, and those servers are running some sort of hypervisor and they're running virtual machines. We'll say that the servers are the nodes here connecting into the leaf switches. And notice the redundancy. Each server connects into more than one of the leaf switches. And we might have in this data center environment, we might have different racks, and we can have what's called a TOR switch, a top of rack switch that interconnects all the switches within that rack. That's an example of a spine switch. A spine switch is going to interconnect our leaf switches. Now notice what's happening here. Every leaf switch connects to every spine switch. That means if I want to go from one leaf switch to another leaf switch, maybe to go between servers, I only have to go through one spine switch maximum because I'm connected to every spine switch. And if we think about this two-tier architecture, this spine leaf design, logically, this is like having a single switch. You could think of that collection of spine switches as the backplane of our logical switch. And our leaf switches are much like the ports on our logical switch that connect out to our end devices. And again, this is commonly seen in data center environments to give us optimal traffic flow and lots of redundancy between our servers. In this video, let's consider an on-premise versus a cloud design when it comes to our data centers. For many years, companies have had very large rooms where they've had maybe raised floors with HVAC and lots of power and redundant power and racks of servers. They've stored their data locally. Prior to that, there were server farms. But a lot of companies have internal data centers. However, there's a lot of expense involved in maintaining the power and the servers themselves. So what a lot of enterprises are now doing, they're migrating having the data centers on site or on premise. They're migrating those data centers to the cloud. Maybe they partner with a cloud provider such as Amazon or Google or Microsoft, and they use those virtual servers up in the cloud to store their resources. One design question that comes to mind if we do move to the cloud with our data is, how do we access that data securely? Well, one option would be to send traffic over the internet. The challenge there is the internet tends to be an untrusted network. But we can send our data securely over the internet if we use some sort of a VPN, a virtual private network, where we're going to be doing some encryption of our data. That way, if anybody intercepts the data, they're not going to be able to read it because it's all encrypted. Another option besides using the internet is to use some sort of a private wide area network connection. A couple of examples there would include MPLS or Metro Ethernet. Now let's take a look at a few design considerations for on-premise versus cloud. First of all, with a cloud deployment, we don't need to have all this redundant power at our site. We don't have to have all the UPSs or generator backup. We don't have to purchase the hardware, in other words. We don't have to go out and buy these massive servers and racks. We don't have to use floor space in our building. And also with a cloud deployment, we pay for the resources that we use. Instead of necessarily buying a server that we might do for an on-premise design, we can just pay for the usage of a virtual server up in the cloud. However, there are arguments for keeping data on-premise as well. For example, with on-premise deployments, it might be easier to meet compliance requirements, where maybe we have backups taken every so often, or we've got the servers physically secured. Another consideration for an on-premise deployment is that it might be able to better ensure a good user experience because we can control the bandwidth coming into our site. We don't really have that much control of the cloud provider. We might be able to monitor performance better if things are on site. And what a lot of enterprises are doing, realizing that in some cases it's better to have the data on site, in some cases it's better to have the data in the cloud. What a lot of enterprises are doing is they're using a hybrid deployment. That's where we're combining on-premise for storage of some data, and cloud for the storage of other data. And another challenge we might have with a cloud deployment is if we want to switch cloud providers. Here, let's say that this enterprise is going to be selecting between these three cloud providers 1, 2, and 3. Well, there could be a lot of administrative overhead to try to switch providers to stop peering with one provider and start peering with another provider. But if we want a bit more flexibility with that, what we can do is have an inter-cloud exchange. This is a service that a company might offer us where we can connect just to them. We peer with the inter-cloud exchange, and then they peer with the different cloud providers. And if we say, I just decided because of a rate increase that I want to switch from cloud provider 1 to cloud provider 3, it's their responsibility to do that re-peering. All we've done is peered with them, and we don't have to worry about re-peering with another cloud provider. That's a benefit of an inter-cloud exchange. And that's an overview of some considerations for an on-premise versus a cloud design. Let's consider how to make our network more redundant in this video. The big goal that a lot of network designers have is called the 5 nines of availability. That means that we're up 99.999% of the time. And if you do the math, that translates to only about 5 minutes of downtime per year. However, if we do want to achieve that level of redundancy, we have to realize it's probably going to increase costs because we're going to have redundant components. We're going to have redundant power, maybe with a UPS, maybe with a generator. We might have redundant routers to give our end devices more than one gateway that they could use to get out to the rest of the world using a first hop redundancy protocol that we'll discuss in our next video. But those are the types of things that we have to consider if we want a redundant design. And you need to decide, is the increased cost justified by an incremental improvement in uptime? And if we do decide that we want to have fault tolerance in our design, which we're going to define as the ability of a device to continue operation even if one of its components were to fail, if we decide that we want fault tolerance, we need to realize that this might impact performance. Instead of having 2 routers share the load, we've got one router that's bearing the burden that 2 routers used to have. And it can increase complexity because of all of the redundant connections. It can make it more difficult to troubleshoot. As a super simple example, consider a network where we've got 2 connections going out to the internet. Well, this is good in that it can increase throughput. We can send some traffic through one ISP and some traffic through another ISP, and it can also provide redundancy. So if we did have a link that were to fail, we could continue using the other link. Even in the LAN portion of our network, we could add some redundant links. Consider a server connecting into a switch. Some servers support what's called NIC teaming, where we have multiple network interface cards connected into a switch. That's going to give us more throughput and redundancy. And remember your CCNA studies where we talked about ether channel or port aggregation? Yeah, we can have port aggregation between our switches. Again, it's going to increase throughput because of load balancing, but if 1 or 2 or even 3 of those links we see on screen were to fail, we are still going to fall back and use any remaining links. Something else we could do to increase uptime is to have redundant servers. We could have a cluster of servers, each of which contained the same information. And that would let us maybe take one server out of service and do some maintenance on that. And by having multiple servers containing the same information, we could load balance across all those different servers. We could have a load balancing appliance that let us share the load. And it's going to give us redundancy because if one server were to fail, then another server can take over. So we're going to get load balancing and we're going to get redundancy. We're going to get better maintenance windows where we can take something out of service. And another big conversation surrounding redundant design is what we do for disaster recovery. First, here are a few different types of backups that I would want you to know about. First is a full backup. This is where we're making a full backup, as the name suggests, of all the data on our server. And whatever our backup media is, whether it's some sort of external hard drive or flash storage or even a tape, we're going to be making a full backup of a server's storage every time we do a full backup. And that could start to consume a lot of backup resources, and it could take more time. So what we might want to do instead is have a differential backup. And I shouldn't say instead, we can add on a differential backup to a full backup. For example, let's say that we do a backup on Monday night and it's a full backup. Well, on Tuesday night, some of the data has changed during the day on Tuesday, and we can do a differential backup, and that differential backup is just going to back up the data that has changed since the previous full backup. That way, that backup is really quick, and we're not going to consume as much backup media. It's going to take a little bit longer to restore because now we have to restore two backups. We've got to restore the full backup, and then we have to overlay on top of that the differential backup. Yet another option is an incremental backup. This is going to back up all changes since the last full backup or the last differential or the last incremental backup. So for example, if we had that full backup again on Monday night, if we were just doing differential backups, the Tuesday night backup would be changes that had been made since the last full backup. So Tuesday's changes basically. But if we just stuck with the differential backup and we took another backup on Wednesday night, it would be everything since, again, the last full backup. It would give us all the changes on Tuesday and Wednesday in that backup. It's different with an incremental backup because it's only going to go back as far as the last full or differential or incremental backup. So let's say that I took a full backup on Monday night, I did a differential backup on Wednesday night, and I did an incremental backup on Thursday night. The Thursday night backup would only include changes made since the Wednesday night differential backup. The Wednesday night differential backup, that would contain all the changes made since the last Monday night full backup. And an incremental backup can be performed faster and take up even less storage than a differential backup. The downside is when it comes time to restore, now we've got to restore a full backup and potentially a differential backup in addition to an incremental backup. Another type of backup we might take if we're using a virtual machine is called a snapshot. This is going to back up an entire server, including state information. If you want to return your server to a specific state with a specific set of files, a specific configuration, you can take a snapshot inside of your virtual machine's hypervisor. One of the downsides to this, though, is we're not able to restore a single file from a snapshot. We're restoring the entire server. Now, let's talk about disaster recovery options. If we've got an enterprise data center and we had some sort of a natural disaster or maybe a fire, something that actually destroyed the data center, what options do we have for getting things up and going again? Well, there are three main options. One option is called a cold site. At a cold site, we have an off-site location, something that's not been damaged by the fire, hopefully, or whatever other natural disaster may have occurred. And in that cold site, we've got floor space available, we've got power, we've got an HVAC system, but in addition to just the power and the HVAC and the floor space, we don't have any equipment. So it's going to take quite some time to recover if we just have a cold site. We're going to have to install servers there. We're going to have to reinstall from backups. It's going to take a while, but it's less expensive to have just a cold site because you're not buying redundant data center equipment. To lessen the time it's going to require to recover from a natural disaster like that, we instead might have a warm site. With a warm site, we still have an off-site location that's been identified. We have power, we have HVAC systems, we have appropriate floor space, but this time we've got the server hardware. We don't have to install the server hardware in this empty room like we would with a cold site. So here the delay would be simply restoring from the backups that we had taken. But if downtime is going to really impact our company's finances, we might decide that it's justifiable to have a hot site. This is what we had when I worked down at Walt Disney World. We had our main data center. It was about 200 yards north of Fantasyland, and we had a hot site in the tunnels underneath the Magic Kingdom called the Utilidors. And there was fiber optic connections. And with a hot site, not only do you have power and HVAC, and you've got your floor space, you also have server hardware and synchronized data. That means every time there is a change to the main data center, that change is immediately written to the hot site. So now if the data center were to go offline, you're still up and going. You've got a hot site with up-to-date data. Now, a few terms I want you to know that surround network redundancy. One of them is an SLA, a service level agreement. This is what we tell our users that we're guaranteeing them about how long a system is going to be down if a disaster were to occur. Another metric that you want to know about is the recovery time objective, or an RTO. This can be part of your service level agreement, and it's going to be the maximum amount of time that we're going to be offline after a disaster. And how much data we're going to lose, that's going to be defined by the recovery point objective, or the RPO. That's the maximum amount of data that we might lose during a disaster because we haven't taken a backup in 12 hours. Well, that might represent the maximum amount of data that we're going to be losing. And when you're buying equipment to make your network more redundant, you should consider the mean time between failures. What is the average amount of time between failures of a particular router or switch or UPS as an example? And also consider, how long does it take to fix something if it goes down? What is the mean time to repair? Those are a few network redundancy considerations to think about when you're doing your network design. Again, you've got to weigh the cost of adding redundancy against how valuable that extra little bit of redundancy is going to be to your company. You want to think about some of the drawbacks, how we can maybe overburden a backup piece of gear, how it's going to be more complex to troubleshoot. You need to think about what kind of backups you're going to be taking. We talked about 4 different types of backups in this video, and also have a disaster recovery plan. If there were a natural disaster at your main data center, what would you do? Do you have an offsite location identified? And if so, is it an empty room? Is it a room with servers in it? Or is it a room with servers that are actively synchronizing data with your primary data center? And that's a look at some network design considerations when it comes to redundancy. In this video, we want to get an overview of FHRPs. Those are first hop redundancy protocols. And there are 3 of them that we need to know about in our Cisco environment. There is HSRP, VRRP, and GLBP. First, let's take a look at HSRP, and that's going to help us better understand what these FHRPs are about. The idea behind a first hop redundancy protocol is making the first hop, in other words, the default gateway as we go from our subnet out to the rest of the world. We want to make that first hop redundant. For example, take PC1 on screen. It wants to get out to the internet, and we could physically point PC1 to a default gateway of 10.1.1.2. That's the IP address of R1. But that suddenly becomes a single point of failure. If R1 goes down, suddenly we don't have another way to get out to the internet. We could go via R2, but PC1 doesn't know about that. It would be great if we could have a virtual router that we point to that doesn't go away even if R1 goes away. And we're going to have this virtual router in this example with an IP address of 10.1.1.1, and that's what we point to as our default gateway on PC1. Notice that's not the IP address of either R1 or R2, but we could say that R1 is going to be the active HSRP router servicing that virtual IP address, and normally we're going to be able to go via R1. But if R1 goes down, R2 is going to be our standby router. Which begs the question, how does R2 know that R1 is still there? Well, by default, and we can adjust this, by default, we're going to have R1 send a hello message over to R2 every 3 seconds. This exchange of hello messages lets R1 and R2 know about one another and know that they're still there. And if we haven't heard from R1 for a period of time, which is by default 10 seconds, R2 is going to say, I think I probably need to take over. But normally, we're going to have PC1 send traffic up through R1 to get out to the internet. But if something does happen to R1 and R1 goes down, then after 10 seconds by default, we're going to have R2 take over as the active router, and subsequent traffic from the PC out to the internet is going to go via R2. That's essentially what a first hop redundancy protocol does for us. Now, later on in this course, we're going to get into a detailed configuration of HSRP, and we'll get into the detailed specifics behind it about how the MAC addresses work and what multicast address we're using and the different versions of HSRP. But for now, in this introductory video, we just want you to understand the distinction between HSRP, VRRP, and GLBP. Now, HSRP, I do want you to know, is a Cisco proprietary protocol. If you're in an all Cisco environment, this might be your first hop redundancy protocol of choice. If you're in a mixed vendor environment, however, you might turn to VRRP. That's Virtual Router Redundancy Protocol. It's very similar in its mission as HSRP. We're still going to have this virtual router to which we point, and in this example, we still have a default gateway of 10.1.1.1 assigned to that virtual router. Something's different here, though. Notice the gigabit 0/1 interface on R1. Did you notice that that's the same as our virtual router's IP address? That's right. That's something that VRRP can do that HSRP cannot do. We can have the physical interface of a router be the virtual router. And if R1 goes down, we'll say that R1 is the master. We don't say active with VRRP. It's the master router instead of the active router, and it's a backup router instead of a standby router. But if R1 goes down, R2 can take over servicing that virtual IP address. Now, you don't have to have the virtual IP address be the physical IP address of an interface. In fact, I kind of think it's a best practice not to do that, but you can, and I wanted you to know that that's a possibility with VRRP. And the hellos work a little bit differently. Instead of having a hello time, which defaults to 3 seconds with HSRP, we have an advertisement interval used to communicate between our routers with VRRP, and it defaults to 1 second. And instead of having a hold time that defaults to 10 seconds, we have something called the master down interval. And again, in an upcoming video, we're going to dive deep into VRRP, and we'll go through the calculation of that master down interval. It's a little bit convoluted. We have to calculate something called the skew time, and we'll get into all that later. But for now, just realize that we're advertising to one another every 1 second. And it works just like HSRP does, in that normally we're going to be going through R1 to get out to the internet. But if something happens to R1, R2 is going to take over as the master router, and subsequent traffic to the internet is then going to go through R2. Now, we've got one other first hop redundancy protocol to talk about, and it's also Cisco proprietary. So out of these three that we're talking about HSRP, VRRP, and GLBP. VRRP is the only one that is an industry standard. The others are Cisco proprietary, but this one honestly is my favorite. And the reason GLBP is my favorite, Gateway Load Balancing Protocol, is that in addition to giving us redundancy, it, as the name suggests, gives us load balancing. And here I'm giving you a basic example of just 2 clients and 2 routers. Now, we still have a virtual IP address of 10.1.1.1 that we're pointing to as our default gateway for both of these PCs. But when a PC wants to go out to the rest of the world and it knows the IP address of a default gateway, it has to also learn the MAC address of that default gateway. And how does it learn that? It sends out an ARP broadcast, an address resolution protocol broadcast, to say, hey, can somebody tell me the MAC address corresponding to this IP address? And with HSRP and VRRP, as we'll get into in a later video in this course, there is a MAC address that gets handed out based on the HSRP or VRRP group number. But here, with GLBP, we're going to give different answers to the same question. I mean, think about this. What if PC1 pointed to R1 as its way out to the internet? And what if PC2 pointed to R2 as its way out to the internet? Now, they're both pointing to the same default gateway. They're both pointing to 10.1.1.1, but what if they pointed to different MAC addresses? Maybe PC1 pointed to the all1's MAC address. That's R1. PC2 pointed to the all2's MAC address. That's R2. That would give us, in addition to redundancy, that would give us load balancing. And there is a router with GLBP that hands out these MAC addresses. It's called the Active Virtual Gateway, or the AVG for short. When it receives an ARP broadcast saying, hey, can you tell me the MAC address corresponding to this virtual IP address? One time, it might hand out R1's MAC address. The next time, it could hand out R2's MAC address. And by the way, you can have a maximum of 4 routers in this GLBP group. So we can hand out the MAC address of R3 and then R4, and then go back to R1, R2, R3, R4, and so on. It could go in a round-robin cycle, which is the default, by the way. And that's going to give us some load balancing. So in this example, R1 is the AVG. But both routers, R1 and R2, they're capable of forwarding traffic off of the local subnet out to the rest of the world. So those routers are given the name an AVF, an active virtual forwarder. They're capable of forwarding traffic off of the local subnet. Now let's go through an example. Let's say that PC1 wants to get out to the internet, so it's going to send an ARP broadcast up to R1, our AVG, our Active Virtual Gateway, and say, hey, can you tell me the MAC address for 10.1.1.1? R1 gets that, and then it's going to respond by saying, yeah, the MAC address is the all ones MAC address. PC2 is now going to ask the same question of our AVG. It's going to say, hey, what's the MAC address of 10.1.1.1? But this time the response is different. This time it says, oh, that's the all twos MAC address, which is R2. That means when PC1 wants to get out to the internet, it's going to be going to the all ones MAC address of R1. And when PC2 wants to get out to the internet, yeah, you guessed it, it's going to go via R2's MAC address, the all twos MAC address. That's the distinction between HSRP, VRRP, and GLBP. Now with GLBP, I said by default we're going to be doing a round robin load balancing. Well, let's talk about the other options. The default is we'll just take turns. We'll go to the first router in the group and the second and maybe the third and the fourth. Again, we can have a maximum of 4 routers in this group. But you might have a situation where, for whatever reason, you want a specific host to always use a certain router, if it's available, to get out to the internet. So we could have a rule set up, a host-dependent rule that says this host is always going to use this gateway, or it's going to prefer to use this gateway to get out to the internet. Or maybe we have routers with different capabilities. We've got a very high-end router, perhaps. It's got a lot of horsepower. Maybe it's one of the newer third-generation ISR routers, like one of those 4000 series routers. And maybe we've got some older routers as well. Maybe we've got a 2800 series router sitting around that's not nearly as powerful. Well, what we can do is distribute the load based on the router's capabilities. We could do weighted load balancing. For example, if I assigned a weight of 50 to R1 and a weight of 100 to R2, then that means my Active Virtual Gateway would be handing out R2's MAC address with a weight of 100 twice as often as it would be handing out R1's MAC address, which has half the weight, a weight of 50. That's going to give us weighted load balancing. And again, later on, we're going to talk in depth about the configuration of HSRP and VRRP, but the Encore exam blueprint doesn't ask us to know how to configure GLBP. You'll get into the configuration of GLBP if you continue on in your studies. For example, if you go after the CCIE Enterprise Infrastructure Lab, that's a time where you would learn more about GLBP. But for the Encore exam, I want you to know what these 3 FHRPs are at a high level that we've covered in this video, and then in upcoming videos, you're going to learn the details and the configuration and the verification for HSRP and VRRP. If we have a router with a couple of route processors, we'll call them RP1 and RP2, we could have redundancy within our router chassis. But there's a challenge. If route processor 1 is currently active and we have a neighborship with another router, maybe OSPF, maybe EIGRP, but we've got a neighborship with another router, if RP1 were to go down, that primary route processor, and we failed over to RP2, what might happen temporarily anyway is we're going to lose that neighborship. And we're going to have to reform another neighborship between our second route processor, RP2, and our neighbor, which in this case is R2. That's the main issue. We're trying to prevent that reestablishment of a neighborship when we're failing over between a primary and a secondary route processor. To address that main issue, we can use a feature called SSO, or Stateful Switchover. With SSO, we are continually sending configuration and state information between the primary and the secondary route processor, meaning that if we did lose the primary route processor, we would almost instantaneously have a neighborship that's still up and available between our backup route processor and our neighbor. But there's a secondary issue. Even though we're maintaining our neighborship thanks to SSO, we still might drop some packets initially. And the reason is that backup route processor does not have an IP routing table. It doesn't know how to forward packets yet. It has to reconstruct that routing table. But we can add yet another feature to prevent that from happening. What we can do is use SSO in conjunction with NSF, which stands for nonstop forwarding. Here's how that works. In addition to having the config and state information synchronized, we're also going to have the Cisco Express forwarding information or Ceph, that information is going to live in memory in the router. And if we did lose our primary route processor, that information that's in memory could be used by NSF, nonstop forwarding, to make forwarding decisions. So we don't have to start with an empty routing table. We've got that Ceph database that can be active and can be used until we can construct our own IP routing table. But that's the benefit of using both SSO, stateful switchover, in conjunction with nonstop forwarding, NSF. Again, SSO, that's going to help us maintain adjacencies or neighborships between our neighbors, and we couple that with nonstop forwarding so that we can make routing decisions immediately after that failover. As we're installing a wireless network in an enterprise environment, we probably need more than just one access point. And there are two basic schools of thought when it comes to managing multiple access points. One is to use autonomous access points. With autonomous APs, we manage each access point individually. They each have their own unique IP address. We go to each one and maybe configure them with identical wireless network names or identical SSIDs, and that allows our clients to roam from one access point to the other. However, it's just not scalable to manage individual access points if we have hundreds or even thousands of access points. So typically in an enterprise environment, we're going to use lightweight access points. With lightweight access points, we're going to be able to configure and control multiple access points from a single wireless LAN controller. And the traffic typically goes from one access point through the wireless LAN controller and then out to the egress access point. And the protocol that we used to use between a wireless LAN controller and an access point was called LWAPP, the Lightweight Access Point Protocol. But in today's networks, you're much more likely to find CAPWAP. That stands for Control and Provisioning of Wireless Access Points. And since we're talking about enterprise networks in our discussion, our focus is going to be on lightweight access points. And in this video, we're going to consider a few different deployment options for lightweight access points. One is to have a distributed wireless LAN controller deployment. That's where we might have access points in our different buildings on campus, and the wireless LAN controller or controllers controlling those access points would be local to those access points, maybe in the same building. That's an example of a distributed wireless LAN controller deployment. However, we might have an enterprise and it has lots of buildings, and one of those buildings is designated as a data center. Well, perhaps we put our wireless LAN controllers in that data center and allow the access points from around the enterprise to communicate with that centralized repository of wireless LAN controllers. And those controllers could be physical devices that are rack mounted, or Cisco allows us to virtualize our wireless LAN controllers and run them as a VM, a virtual machine. And we could do that in our data center, or since they can be virtualized, we might connect out to a cloud provider, perhaps through the internet, and we could install as virtual machines in that cloud provider our wireless LAN controllers. And that would allow us to have a cloud WLC deployment where our access points within our enterprise were being configured and controlled by one or more wireless LAN controllers that lived in the cloud. And one final option I'd like you to consider is a branch office. Let's say that we've got this remote branch office and perhaps it only has a couple of access points. And we might conclude that it's not worth putting wireless LAN controllers in that branch office. What we could do instead is just leave the wireless LAN controllers back at the campus data center and have those access points be controlled by that campus data center collection of WLCs. However, as we look at traffic patterns, it doesn't seem terribly efficient if I'm going from one VLAN in the branch office to another VLAN in the branch office for that traffic to traverse the WAN and then come all the way back to the branch office. Well, we don't have to do that because Cisco gives us the option to use the Cisco Flex Connect feature. This is going to allow us to configure and control a remote wireless network. And there are a couple of ways that we could do this. One, which is probably not recommended in this instance, is central switched. This is going to operate as we would traditionally operate in an enterprise environment, where all of our wireless traffic goes back to the wireless LAN controller, but that's going to require that we span the WAN and take up WAN bandwidth when really the traffic needs to stay local to the branch office. And as a result, this is typically not the recommended mode of operation for a situation like this. Instead, we can use local switched. With local switched, that end user traffic can stay local to the branch office, and the access points will be intelligent enough to properly forward that end user traffic. And I emphasize that this is end user traffic that's staying local because we're still going to be using CapWAP to communicate with that centralized repository of wireless LAN controllers back at the data center. So we are going to be going over the WAN, but just for control and management traffic. And that's a look at a few deployment options for wireless LAN controllers in an enterprise network. If we have multiple wireless access points in an enterprise network, a benefit that we get besides just wireless connectivity for our users is the ability to locate a device. We can use a feature called location services. And a common misconception about location services is that we're just checking to see which access point that a client is associated with right now, and we assume that that's generally their location, where that access point is. But that's not terribly specific. What we do instead with location services is we can measure the signal strength from multiple access points. This signal strength is measured as RSS, received signal strength. And let's say that this laptop on screen is in the proximity of 3 access points. Well, we can take a look at the received signal strength from each of those access points. And if we have a floor plan showing where those access points are installed, then it can mathematically be determined fairly precisely where this client is right now. Not just at the location of an access point, but at a location that would result in these received signal strengths from these specific nearby access points. This might be used, for example, in location-based advertising. If you've ever been in a shopping area and as you go from one location to the other, you might get push notifications about a sale going on in a store, and as luck would have it, you're directly outside that store. That's what can be accomplished with location services. You can be marketed to based on your location. But in our enterprise networks, it's great for asset tracking or troubleshooting to see where do our devices reside right now. And Cisco accomplishes this using RTLS. That's real-time location services. And if we take a look at Cisco DNA Spaces, it looks much like this. If we have a floor plan and we have positioned our access points correctly on this floor plan, we're going to be able to see to a fairly high degree of certainty the current location of our wireless clients. And it's not just Cisco DNA Spaces that gives us this, it's also on Cisco's Meraki platform. And here's a look at what that might look like. Very similar. We have a floor plan and we're able to see a fairly precise location for our different client devices. And that's all made possible thanks to location services. A design consideration we have for enterprise wireless networks is client density. Client density refers to the number of clients we need to service within a particular wireless coverage area, and it's an inverse relationship between the number of clients that we can serve and the possible network performance for each of those clients. Here in this example, we just have 3 clients, and they get to share the resources of that wireless access point. But as we start to add different devices to that access point, then the slice of the bandwidth pie available to each wireless client is going to decrease. And let's say that we do need to increase our client density, because today we might have one user that's using multiple wireless connections simultaneously. They might walk into their office carrying a smartphone, which is going to be connecting to the wireless access point. They might have a smart watch that connects to that access point. They might be carrying their laptop and a tablet, each of which can connect to that wireless access point. So it's a lot easier to have a higher client density in today's networks. And as we're thinking about client density, we need to keep in mind overlapping channels. Here we have one access point, and it's using a particular channel, and it has this coverage area that you see highlighted. But if we need a higher client density, and we start installing other access points in close proximity to the first access point, they're all going to be using part of our available radio spectrum as well, and hopefully they're using non-overlapping channels to avoid interference, but we only have so many non-overlapping channels available to us. We only have 3 in the 2.4 gigahertz range. We have more if we're using the 5 gigahertz range, or even more if we're using the 6 gigahertz range. And if we do have our access points physically packed tightly together like this, and we might be using some overlapping channels, one option to still give us the performance of multiple access points while avoiding overlapping channels is to reduce the signal strength where one access point is not interfering with another access point. And when we're selecting the number of access points to use in a network, we need to consider the specifications of the AP we're selecting. Things are going to vary widely depending on the specific model of AP. One AP may have more radios than another AP. They may support different wireless standards. For example, we can have more non-overlapping channels using the 6 gigahertz band offered by Wi-Fi 6E as compared to Wi-Fi 6. Of course, that's assuming our clients can support Wi-Fi 6E. Another factor that impacts our client density is the anticipated number of simultaneous communication streams that we need to support. Is it a classroom where everybody is going to be active at one time going to a particular website that the professor is lecturing about? And what are the bandwidth demands of a particular application? Is it text-based, or is everybody streaming 8K video? And in a particular design, if you decide that you do need to increase the number of APs, what can you do? Well, you can increase the number of APs physically, and to help prevent one AP from interfering with another AP, you can reduce the transmit power of those APs. And if you're still running into an overlapping channel issue, something else you might consider is your channel bonding. For example, let's say that instead of using a single channel that's 160 megahertz in width, which is bonded together 8 20 megahertz channels, what if you broke that down to 4 40 megahertz channels? That would allow 4 different access points to use separate 40 megahertz channels, where before we had just one access point using one 160 megahertz channel. And as I hinted at earlier, if your clients support it, you might consider using Wi-Fi 6E, which adds on to the Wi-Fi 6 standard by allowing you to use the 6 gigahertz band, giving you an even wider range of non-overlapping channels. And that's a look at a few design considerations regarding client density for our enterprise wireless networks. One of the things we love about managing lightweight access points as opposed to autonomous access points is that if we have a large wireless network, maybe we have an enterprise location with multiple buildings and multiple access points, with a lightweight access point approach, we can go to a wireless LAN controller and configure lots, if not all of the APs in our enterprise. That's as opposed to individually configuring them with autonomous access points. However, in an enterprise network, we probably have some access points that need to be configured differently than other access points. So the goal is to be able to have a granular level of control on our enterprise's access points without having to go to the extreme of configuring them individually. For example, let's say in these two buildings, only that top access point in building 1, only it should be advertising the SSID or the wireless network name for the research and development department. The other 7 access points should not be advertising that. Maybe all of the access points in building 1 should support the 5 and 6 gigahertz bands, but not the 2.4 gig band, while all 3 bands should be supported in building 2. And let's say that our CapWAP settings, like different timers, are different between the different buildings. And in this video, we want to consider a strategy for accomplishing a goal like this. And the solution is to segment our wireless networks with profiles, tags, and then we can group access points together that have the same set of tags. First of all, let's consider a profile. And there are different categories of profiles, and each category describes a particular characteristic of our wireless network. And within that profile describing that characteristic, there are a set of parameters that we can set. Let's take a look at the profiles that Cisco supports. One type of profile is a wireless LAN profile, sometimes called an SSID profile, because it controls what SSIDs or wireless network names get advertised. And this is not a comprehensive listing, but it controls things such as how the client authenticates with the network. Is it going to be using a pre-shared key? Is it going to be using 802.1x to authenticate with a radius server? Or is it going to be doing web auth? Another type of profile is a policy profile, and as a couple of examples, it contains information about VLANs and quality of service settings. There's the AP profile, or some literature calls it the AP join profile. This can have information about our CapWAP settings, such as various timers. It can have information about our power over Ethernet settings. And if we're using Cisco Flex Connect, which allows us to have a wireless LAN controller maybe at the headquarters and control wireless access points that live at remote sites, well, those settings can be specified in the Flex profile. There's an RF profile for radio frequency. This can control what channels we're going to be using and the transmit power levels. Those are the profiles that we can have, different categories of wireless LAN characteristics, and then we can group these profiles into different tags. And there are three types of tags. The first one is a policy tag. This is going to link the wireless network name, the SSID, the service set identifier. It's going to link that SSID to the policy profile. Our second of three tags is the site tag, and that tells us whether or not an access point is being controlled with a local wireless LAN controller, that will be local mode, or if it's being controlled by a wireless LAN controller at another site, running in Flex Connect mode. And this site tag also contains the AP join profile and the flex profile that might be applied to an AP. And finally, we have the RF tag, the radio frequency tag. This can be used to specify what bands of frequencies we're using, as well as some of the settings within those bands. And what we can do is take a set of tags and apply them to an access point. And we might have multiple access points that need the same set of tags. Well, we could logically group them together in a group. A group is a collection of one or more access points that need a common set of tags. Remember that top access point in Building 1? It was the only access point that was supposed to advertise the research and development SSID. So we might put it in its own group and give it its own set of tags. And the policy might be called Policy RD for Research and Development. And we might have the same site tag for all 8 of these access points because they're all at the HQ site. And we might have an RF tag of 1. And that could be applied to all of the access points within Building 1, remembering that those access points do not support the 2.4 gig band, but the APs in Building 2, they do. And for the remaining APs in Building 1, they could be put in a group and assigned this set of tags. The policy could be the general policy for all HQ access points, with the exception of the R&D access point. And all of our access points, we said, are going to be sharing the site HQ tag. And we'll also give this the RF1 tag. It does not support the 2.4 gig band. And then we can group together all of the APs in Building 2 and give them this set of tags. They can all be assigned the policy HQ tag. And just like all of the APs in Building 1, everybody's sharing the site HQ tag in this example, but the APs in this building, they should support that 2.4 gig band, so we'll give them a different RF tag, RF2, which will include the 2.4 gig band. And that's a look at how profiles, tags, and groups give us the best of both worlds when we're comparing autonomous versus lightweight access points. By using profiles, tags, and groups, we don't have to configure all of the APs one at a time, but we can do granular configuration when we need to.
Enterprise WAN connections allow us to interconnect main offices with branch locations, among other things, and that allows us to share resources. We can share access to centrally located data, services, or applications. Traditionally, dedicated circuits have been used to achieve this connectivity, things such as frame relay or MPLS. Although these provide reliability and security for the connection, our modern networks require some rethinking of this. Cloud usage, as we know, is on the rise, so we need ways to simplify the management of wide area networks. We also need a way to include our cloud resources. More and more enterprises are using cloud-based storage, and that's why SD-WAN is also on the rise. SD-WAN stands for Software Defined Wide Area Network. As the name suggests, this uses software to control and to manage the interactions between branch locations and our central resources. When we're looking at the function of SD-WAN, one of the big advantages is that there's no longer the need for backhauling your traffic. And when we say backhauling your traffic, we mean that historically with these dedicated circuits, traffic would have to go from the branch back to the main site, no matter what type of traffic it was, whether that was WAN internet traffic, whether that was traffic destined for shared resources, whatever that is, all the traffic was backhauled over that WAN connection to the main office. So that offers the potential for saturation of the WAN connection. Instead, we want to look here at what SD-WAN allows us to do. If we take a look at a very simplified topology, we can see that we have a branch location connected over an MPLS circuit, which is a traditional WAN connection method, that's connected back to a data center. At the data center, we have some advanced security and inspection happening. So that's why we would tunnel all of our traffic from the branch back to the data center for inspection. Now, in this traditional WAN setup, all of the traffic from the branch is backhauled to the data center for those security services. That includes traffic destined to the cloud or the public internet and traffic destined locally within the organization as well. So as we mentioned, and as you can probably imagine, this can cause a myriad of performance issues and delay. Depending on your circuit speed, it can cause some bandwidth issues on the MPLS connections. SD-WAN addresses this by its ability to interact with all kinds of cloud applications. More and more, our applications are going cloud-based. Think of how cheap and easy AWS storage is now, and how Office 365 has turned to a cloud platform for enterprise email access. SD-WAN can easily interact with applications like AWS, Dropbox, Azure, Office 365, and many, many more. So this means that hosting applications in either public or private clouds will allow direct traffic between the cloud application and the branch location. It will allow that rather than backhauling all of the traffic through a central data center. So that's a big reason that we're moving more and more toward SD-WAN. SD-WAN solutions can intelligently control the path of traffic in order to optimize traffic flow and to reduce unnecessary bandwidth in our networks. Now, you might be wondering, what happens to the security inspection services, since that traffic is now not being routed through the data center any longer? That's been addressed as well, because most SD-WAN offerings now provide end-to-end traffic encryption and inspection. Additionally, more and more next-generation features are being added, things such as anti-malware systems and botnet intervention, many features that you would see on next-generation security devices. Another big advantage of SD-WAN solutions is that they provide traffic transport independence. And in order to understand that, we need to understand the difference in an overlay network and an underlay network. An underlay network is simply the physical network infrastructure responsible for the delivery of packets. We see that here in this example. We have several sites and a data center, all interconnected by physical infrastructure. SD-WAN, on the other hand, that is a type of overlay network. And overlay networks are simply a virtual network built on top of an underlay network, or built on top of the actual physical infrastructure. Overlay networks aren't anything new. Those have been around for a long, long time. Overlay networks even include things like voice over IP or VPNs. Those run on top of the internet as an overlay. With SD-WAN as the overlay network, this gives us transport independence. And by this, we mean that our WAN connections can be made up of all different types of connection combinations. We might have some LTE connections, we might have serial connections, wireless connections, satellite connections, MPLS. It doesn't matter what's running as our underlay network, because SD-WAN solutions can very intelligently and coherently choose the best data path transmission. And that's great news for us as network administrators, because it simplifies our job even further. Now that we understand what SD-WAN is and why that's being increasingly used in our modern enterprise networks, in our next video, we want to take a look specifically at Cisco's SD-WAN solution and how we would see that commonly implemented in an enterprise network. As we take a look at SD-WAN implementation, we want to specifically examine the recommended Cisco-based solution. At the time of this recording, that is Cisco's SD-WAN based on Viptela. Cisco acquired the Viptela company in 2017, which provides a cloud-based SD-WAN solution. This is recommended to be used in conjunction with Cisco's DNA Center, and that will allow you to leverage automation and virtualization capabilities. Within Cisco SD-WAN, we can break this down into 4 planes: the data plane, the control plane, and the management plane, which you're probably familiar with from traditional networking models, and the 4th plane, known as the orchestration plane. This is essentially shared with the management plane. There are 4 different solutions within Cisco's SD-WAN created to manage each of these 4 different planes. The first is Cisco vManage, which is very simply the GUI interface for managing the Cisco SD-WAN solution. This is where you would perform configuration, monitoring, and provisioning. Then there's Cisco's vBond, which controls the orchestration plane. It's the job of vBond to understand how the network is constructed and to make sure all of the interconnected components can work together. One of the big capabilities here is something called zero-touch provisioning. This means that when an SD-WAN capable router is introduced into the network, Cisco's vBond can remotely provision the router from anywhere without the need for an administrator to take any action at all. So that's super helpful for us as administrators. Next, we have Cisco's vSmart, which resides within the control plane. This is thought of as the brain of the SD-WAN solution. As we create policies in vManage, as an administrator creates those policies, the vSmart component is responsible for the enforcement of the policies. Those policies are also shared with other SD-WAN routers and locations in our network. Route information from branch locations are received via the Overlay Management Protocol, or OMP. vSmart can use the known policies against these routes to control the traffic flow through the SD-WAN fabric. And finally, in the data plane, we have the actual WAN edge routers themselves, which are responsible for establishing the network and for forwarding traffic. These devices can be either physical or virtual, or we can have a combination of those. These SD-WAN capable edge routers are referred to as Cisco vEdge routers. Let's take a look at a very common way that we might see this implemented. Here we see a sample topology within which we have a main campus location, a couple of branch locations, a physical data center, and a cloud data center. All of these are interconnected through various means. We see MPLS, we see LTE, and we see satellite connections, creating this network of sites. Again, remember that SD-WAN is an overlay technology, and that provides transport independence. So in other words, it doesn't matter what the physical underlying network infrastructure is. As we see here, SD-WAN can work with any and all of that. At each of these locations, we would have a WAN edge router, a Cisco vEdge device, and these routers form IPsec tunnels with each other in order to create the SD-WAN overlay network. This is going to make up the data plane that we discussed a bit earlier. Also recall that all of the control elements we discussed earlier, Cisco's vManage, vBond, and vSmart. Secure control channels would be established between each of these elements and each one of the WAN edge routers, and that would be used for provisioning and for configuration of the devices. As for the edge routers themselves, these can be either a hardware or software platform. Hardware platforms include Cisco vEdge routers running on the Viptela operating system and certain integrated service router and aggregation service router models. Virtual platforms include the vEdge cloud router running Viptela OS and cloud services router models running iOS XE SD-WAN software. So that's a look at Cisco's SD-WAN based on Viptela and how we would commonly see that implemented in an enterprise network. We previously examined the merits of software-defined networking and how that helps simplify the management and configuration of our infrastructure. Cisco has taken that one step further with something they call software-defined access, or SD access. Let's run down a few advantages provided by software-defined access, starting with the features of Cisco DNA Center. Cisco DNA Center is a key piece of the SD access solution and acts as a central point of management. And that central point is able to automate the deployment and the configuration of network devices. With SD Access and Cisco DNA Center, network device configuration becomes automated. Whether you're deploying one or multiple new devices in the network, DNA Center works as a central hub of control, which allows for super fast deployments. Policy enforcement is another important improvement offered by SD Access. Rather than relying on traditional access control lists, SD Access uses something called Security Group Access Control Lists, or SGACLs. These can be thought of as a group-based policy, and they're much more scalable. If you think about traditional ACLs, those rely on IP addresses and subnets, which can be complicated to maintain or to scale for a larger network. SGACLs used by SD Access, those overcome this limitation through group policies that are based on client identity rather than IP addresses. So we don't have to worry about the scalability. Using those policies make it much easier to scale. Going hand in hand with this is the ability to securely segment the network very simply. Since SD Access sees the entire infrastructure, both wired and wireless, as a single network fabric, it's very easy to segment the network without the need for various firewalls or other complicated access control lists. And network virtualization is also a big plus for SD Access. This allows our single physical infrastructure to be separated into multiple virtual networks. Each of these virtual networks can have their own set of access policies that are created and enforced through SD Access. We can break down the SD Access solution into two main components: Cisco DNA Center, which we've already mentioned, that provides automation and orchestration throughout the network, and something called Campus Fabric. Recall that we discussed underlay and overlay networks in a previous video. The underlay network is our physical infrastructure, and Campus Fabric is simply another example of an overlay network. Specifically, it's a Cisco validated overlay. The Campus Fabric solution ideally will manage the network through use of Cisco's DNA Center. This can also be managed via CLI or API through the netconf protocol and Yang modeling language. We'll discuss netconf and Yang more in depth later in this series, but for now, just know that these are options used to operate the network infrastructure in a campus fabric. The reason that a campus fabric was developed is to overcome traditional campus network issues, things like spanning tree problems and layer 2 forwarding. And it's also an improvement over architectures such as 3-tier or spine and leaf. So campus fabric can really simply be thought of as a next generation campus network where management and configuration is simplified and centralized into a single point. Here we can see a graphical example of what this looks like. We see an actual physical underlay network and the campus fabric overlay network. The campus fabric is what provides our network with segmentation and security features through those policy-based security groups that we mentioned earlier. Also know that the security provided here goes beyond traditional routing and switching security capabilities, because it's recommended that you leverage Cisco's Identity Services Engine to gather contextual user information for those security policies. So here we can see that even though our underlay network is a little more complicated and it has a few more intermediate devices, the overlay network simply sees that as a much smaller and simplified network. So that's just a really easy example of how that works. Now, we've already mentioned that the Campus Fabric overlay can be configured through CLI or API, or it can be fully automated through DNA Center, which is actually the recommended method. So while you can use a Campus Fabric solution and manually configure that through CLI or API, that is not considered to be SD Access when you configure in that manner. SD Access is specifically defined as being fully automated with DNA Center. If DNA Center is not being used, then you simply have a Campus Fabric solution. You do not have a software-defined access solution. So that's just some nomenclature that you should be aware of. So from here on out in this discussion, we're assuming that we're using both a Campus Fabric solution and DNA Center, which we'll generally refer to as SD Access or the SD Access Fabric. You probably won't be surprised to learn that there are three planes of operation in the SD access fabric: the control plane, the data plane, and the policy plane. The policy plane is based on Cisco TrustSec, which will be covered in depth later in this series. TrustSec helps to create the security groupings that we mentioned earlier, so that policies can be based on identities rather than IP address schemes. The SD access control plane is based on the Locator ID Separation Protocol, or LISP for short. LISP is simply an addressing architecture developed by Cisco as a variation of node addressing. So rather than relying on a single numbered address identifier, such as an IP address, LISP creates two addresses for each node, one address for its identity and another for the location where it's found in the network. So LISP is a way to simplify traditional routing and to streamline our network. The SD access data plane leverages a tunneling technology called Virtual Extensible LAN, or VXLAN. This encapsulation is what creates the SD access overlay network. This is UDP-based communication, meaning that any IP-capable device has the ability to forward the information. The VXLAN encapsulation allows for not only Layer 3 overlay networks, but also for creating separate virtual network instances where separate policies can be applied and enforced. So know that the control plane uses LISP data encapsulation, while the data plane uses VXLAN encapsulation. Both of these encapsulations will be examined closer later in this series. If we break down a typical topology structure visually, we'll see four distinct layers in SD access architecture. We can see that the physical layer is, of course, our actual infrastructure devices: routers, switches, our wireless infrastructure, a DNA center appliance, and a Cisco Identity Services Engine appliance as well. In the network layer, we see our underlay and overlay networks. The underlay network includes the settings and protocols used in the physical infrastructure for transporting data packets, while the overlay network is a virtual network that forms a fabric of its own. As we saw earlier in our example topology, this overlay strips out some of the limitations and complexities of the network and makes a more simplified fabric. The tunneling is performed using VXLAN encapsulation to build that fabric. And then we have the controller layer, which consists of Cisco DNA Center and Cisco Identity Services Engine appliances. We can break down Cisco's DNA Center into two main structures here, which are the Cisco Network Control Platform and Cisco Network Data Platform. Cisco NCP is used for automation and orchestration of the physical and network layers, while Cisco NDP is used to collect analytics and historical trends used by the management layer and by Cisco ISE. Cisco ISE, of course, is for identity and security services and is the piece that identifies and places users into those policy groups so that the policies can be enforced throughout the network fabric. Finally, we have the management layer, which is the Cisco DNA Center user interface. This is essentially a centralized dashboard that allows you to view and control your entire network through intent-based networking. The unique thing here is that Cisco DNA Center provides really simple GUI tools for management and deployment, which means that you don't necessarily have to know how to configure each individual network device in order to use this deployment method. Really unique. So now that we understand why SD access is relevant and we know the required pieces of the SD access fabric, in the next video, we'll take a look at a common way we might see this implemented in a real-world enterprise topology. We've discussed what makes up a complete SD access solution. So now let's take a look at a common way we might see this implemented in an enterprise topology. You can see at the very bottom, we have our end user devices, both wired and wireless clients here. The first piece of the SD Access implementation that we'll examine are called the Fabric Edge nodes. This is the layer that provides user access through wired or wireless connections. Not only does this provide a connection point, but this also is where identity and authentication for users takes place. This is where Cisco TrustSec and Cisco ICE are leveraged to enforce security policies and to place users into the appropriate access groups within the network. So these devices sit on the edge of the SD Access fabric, as you can see here, and they provide users a place to connect into the network. We also have what are referred to as fabric intermediate nodes, and there could be any number of these nodes. These are simply the internal routers or switches that are part of the underlying physical structure. They have no role in SD Access other than providing the underlay services using protocols such as OSPF or EIGRP, for example. Remember that the underlay network isn't dependent on any specific protocol. It can be a mixture of all kinds of protocols, and that can be wired or wireless as well. Then we have what's called the Fabric Control Plane node. Remember from our previous video that the control plane uses Lisp encapsulation for node mapping. Lisp contains two namespaces for each node, an endpoint identifier or EID, and a routing locator or RLOC. This particular node would essentially be a Lisp server, and it would contain a database that would be used to resolve these EIDs to RLOCs in order to map the nodes within the network. So the Fabric Edge nodes that we looked at earlier would provide information from our connected clients back to the Fabric Control Plane node so that they could create and update these mappings. Now, this Lisp server would also resolve lookups from those nodes. It's important to note that you'll want to choose a fairly robust device to act as a Fabric Control Plane node, because this is going to contain all of the fabric mappings. So just be aware that there's some fairly stringent hardware and software requirements when you choose this particular node. You want to choose a fairly robust device. And we also have a fabric border node. These are essentially Lisp proxy tunnel routers that allow for external layer 3 connectivity back into the SD Access fabric, so they can communicate policy and identity information between separate domains, whether that's a remote office or maybe a data center. There are three types of fabric border nodes you want to know about. There are internal border, default border, and anywhere border. Internal border nodes are also referred to as rest of company nodes. They connect only to known areas of the organization. These could be a local data center, a wireless LAN controller, or a firewall, for example. Default border nodes are also called outside border nodes. They connect only to unknown external networks, such as the public internet or a public cloud. This would be configured with a default route pointing to the outside world. And anywhere borders combine internal and default border nodes, offering connectivity both to the inside of the organization and outside to the public internet. We can see the Fabric Control Plane and Fabric Border nodes here connected out to our server room. This, of course, will contain our Cisco DNA Center and Cisco Identity Services Engine appliances. And we also see a wireless LAN controller here. So this requires that you have fabric-capable wireless LAN components, by the way. We do want to mention that. Both the access points and the wireless LAN controllers should be fabric capable. One difference to point out here, as opposed to traditional wireless deployment that we've discussed already, it's very common to see a centralized topology in the enterprise. This means that the wireless LAN controller, when it's traditionally placed, is centrally connected to the network infrastructure and has access points dispersed throughout the physical buildings. And when we have that traditional model, all of the control plane and the data plane traffic from the wireless clients is moved from the access point, and it's tunneled through the wireless LAN controller using CAPWAP tunnels. We've talked about those already as well. And that allows the wireless LAN controller to handle everything, both the control plane and the data plane traffic. Now, the difference in that traditional wireless and SD Access wireless, we know that with SD Access, the data plane is distributed using VXLAN. You'll recall that from our previous video. So in an SD access wireless deployment, a fabric AP would establish a VXLAN tunnel with a fabric edge node, and it would do that rather than establishing a CAPWAP tunnel with the wireless LAN controller. Now, it still does have a CAPWAP communication going on. We'll talk about that in just a second, but the VXLAN tunnel that's created here is used to carry data from the access point back to the SD access fabric, where the overlay network can take care of directing the traffic anywhere it's needed. So this is a much more efficient and scalable type of topology for wireless, because the traffic doesn't always have to be carried all the way back to the wireless LAN controller in this model. For control plane traffic, we see that this is still carried back to the wireless LAN controller using CAPWAP, but this time it's CAPWAP encapsulated inside of a VXLAN tunnel. So that's still handled by the overlay network, and you still get the advantage of using the SD access fabric to carry the control plane traffic back to the controller. And of course, this is all managed, orchestrated, and monitored by Cisco DNA Center. This provides a GUI interface where we can create policies and subdivide our network into virtual instances. And we have an automated control platform that's going to assist us with configuration and device provisioning. So that's a look at how SD access is commonly implemented in an enterprise environment and how it interacts with traditional physical network devices to help us improve our networks and to make management of the networks much easier.
In this video, we're going to take a look at some different quality of service or QoS mechanisms. First, let's identify when or if we might need QoS. One time we might need QoS is in a situation like this where we have a speed mismatch. Notice that we're coming into router R1 on a gig link, but we're going out to the IP WAN on a fast Ethernet link. That's a 10-to-1 speed mismatch. And if traffic is coming in faster than we can send it out, that could cause some congestion on the output interface of that router. Or maybe we don't have a speed mismatch. Instead, we have an aggregation point. Here we've got an Ethernet switch and all the ports are running at a gig speed, but maybe we've got a bunch of servers coming into the switch and we're all trying to leave this server farm on a single gig link. We're coming in with multiple gig links and leaving on a single gig link. That could cause some oversubscription of the bandwidth and cause congestion even on a high-speed switch network. The great news is we've got some quality of service mechanisms that can help us out in situations like this. However, if we're congested all of the time, we need more bandwidth. Quality of service is good for periodic congestion. Maybe there are specific times of the day when we're congested. Maybe everybody is coming in at 8 a.m. and they're firing up their computers and they're synchronizing their Dropbox accounts and there's a lot of network traffic, or maybe overnight we're doing a network backup. That might cause some congestion. If we just have those periodic times of congestion, yeah, quality of service might help us out. But if we're congested all the time, we need more bandwidth. And quality of service breaks down into 3 different categories. We have a best effort category that's not strict at all. In fact, I even hesitate to call it a quality of service category because really it's FIFO, first in, first out. The first packet that comes into the router or switch is the first packet to go out. There's no reordering of packets. There's no prioritization. It's just first come, first serve. That's best effort quality of service. Another QoS category we have is diff serve. That's less strict than our most strict, which is the bottom we'll talk about in a moment. But diff serve is short for differentiated services. This is typically what we're going to be using in our enterprise networks. We're going to mark traffic with a diff serve marking. Specifically, it's a DSCP marking, a differentiated services code point marking that's going to identify the relative level of priority and drop probability for a packet. There is a more strict option for QoS, and that's called IntServe, which is short for Integrated Services. The mechanism I want you to know here is RSVP. That's the Resource Reservation Protocol. And it can make a hard and fast reservation for an application. And it can say that during this application, nobody else is allowed to use this bandwidth. Even if this application doesn't need it at the moment, it's reserved. And until that application stops and gives that reserved bandwidth back to the bandwidth pool, nobody else can use it. That doesn't really share bandwidth. It doesn't make the most use of available bandwidth. So typically we go with the less strict option, or diffserve. Now let's take a look at some specific QoS mechanisms. And the first one is classification and marking. And Cisco says that we should classify and mark our traffic as close to the source as possible. As an example, let's say that I'm going to be traveling on an airplane. And currently, I've not earned silver medallion status, or whatever they call it on Delta Airlines. I fly Delta a lot. But imagine the day comes. Imagine the day comes where I earn that frequent flyer status, and I get to get on the plane first, and I go up to the gate agent, and they say, "Hello, Mr. Wallace, before we let you on the plane, can you prove that you're a frequent flyer? Can you produce the boarding pass from the time you went to San Jose and to Orlando and to Austin and to Las Vegas?" No, that wouldn't be efficient, would it, if I had to prove myself every time I got on the plane? So what do? Well, they give me a marking on my boarding pass that says something like Sky Priority, and that tells them that I am a priority passenger. I get to get on first. It's the same thing with our network traffic. Very early on in a packet's travel, we're going to recognize it. We're going to classify it as being a particular type of traffic, and we're going to mark it. But classification and marking by itself doesn't really alter the behavior of packets. We need some other mechanism that's going to look at that marking and make a decision, like a forwarding decision or a dropping decision based on that marking. An example of a mechanism that can do that is queuing, which is also known as congestion management. You might see that in the literature. But queuing is going to influence how a router or a switch forwards packets out of an interface's output queue. Remember when we talked about the speed mismatch a moment ago, and we were coming into a router at a gig rate and we're trying to leave it at 100 megabits per second? Well, what's going to happen to those packets that we cannot send right now? Well, that output interface can reserve some memory called a buffer or a queue, and it can store those packets that we just don't have bandwidth to send at the moment. It can store those packets temporarily in that queue. And then when bandwidth becomes available, we can take the packets out of the queue and send them on their way. Now, if we just did this on a first come, first served basis, that would be the not strict. That would be the best effort flavor of QoS. However, we might want to have a little bit more control over how packets get forwarded out of the queue. After all, that queue is of a finite size. It can only hold so many packets. Imagine that we had this big data burst on the network, and we're flooding traffic trying to go out to the IP WAN, and that queue is filling up, and eventually it's going to fill to capacity. It's going to start to overflow. We're going to be dropping packets, high priority packets, low priority packets. We're dropping everybody. But what if we did something very simple? Let's say that we took that output queue and we divided it into two queues, two sub queues. Maybe we're going to put voice over IP traffic in one queue or one bucket, and we'll put everybody else in the best effort queue or the best effort bucket. Now, the best effort queue, it might fill up, it might overflow, but meanwhile, the voice over IP bucket is not overflowing. We're not dropping voice traffic because we've done this basic queue separation. Now, in the enterprise network, Cisco and he says, "Spock," and Spock comes to the glass and he says, "Ship out of danger," and Kirk says, "Yes." And they go on to have this discussion. He says, "Why did you do it, Spock? Why did you give your life to save the Enterprise?" And I paraphrase here. Spock said, "Don't grieve, Admiral. It's logical. The needs of the many outweigh the needs of the few." And then Kirk says, "Or the one." Well, that's what Weighted Red is doing. It realizes that the needs of the many TCP flows outweigh the needs of the one TCP flow. And it will throw away packets from individual flows. It'll make those flows suffer so that everybody doesn't have to suffer. That's what Weighted Red does for us. Our next QoS mechanism is policing and shaping. Now, together, these are called traffic conditioners, and they will set a speed limit on our traffic. Unlike queuing, which gave us a minimum bandwidth guarantee, policing and shaping give us a maximum bandwidth limit. And policing is a bit more harsh than shaping. If we try to go above a speed limit called the CIR, the committed information rate, with shaping, shaping says, I'm so sorry, I don't have enough bandwidth to send you at the moment, but don't go anywhere. Let me temporarily put you in this queue, and then when the bandwidth demand dies down, I'll take you out of the queue and I'll send you on your way. So shaping is delaying traffic when it tries to exceed the speed limit. Policing by default is much more harsh. It is going to, by default, drop any packets trying to exceed that speed limit, that CIR that we've set. And the reason I have a bowl of soup on the screen is it reminds me of that Seinfeld episode where if you don't order soup correctly, the guy says, "No soup for you, come back 1 week." That's what policing does. It says, "No bandwidth for you, come back." Literally come back, because we're causing TCP segments to be retransmitted. So policing and shaping, or traffic conditioners, they're setting speed limits on our traffic so we don't have a particular traffic type consuming too much bandwidth. And the final category is link efficiency. And this, as the name suggests, is trying to make the most efficient use out of a relatively limited amount of bandwidth. Now, to be honest, this is not nearly as important as it was a few years ago, because now our link speeds are typically higher. We've got gig links all over the place these days. But if you do have some slow link speeds you're dealing with, then you might want to consider a link efficiency mechanism. And what do I mean by low speed? Well, first of all, take RTP header compression. That's one of the link efficiency mechanisms. RTP, that's the real-time transport protocol. That's what we use to send voice traffic and also video traffic. And if you look at the header of a voice packet, it could be 40 bytes in size. If we use a coder-decoder or a codec of G.729, that's a common codec for voice that's going to save bandwidth. If you look at the header and you add up the IP header and the UDP header and the RTP header, it's a whopping 40 bytes in size compared to a payload size of only 20 bytes. That's right, the header's twice the size of the payload. That's not a good ratio. So what RTP header compression will do is it will make this observation. It will say, as we send packets as part of this voice conversation between these two routers, each of the headers have a whole lot in common. All of these headers in this flow have the same source and destination IP addresses. They all have the same source and destination UDP port numbers. They all have the same RTP payload type. Instead of sending all that redundant information, what they do instead is cache it. They make a copy of it and they put it in memory in the routers at each end of the link, and they just don't send that information. We'll strip off that 40-byte header on one router, send it over the relatively low-speed WAN link, and when it gets to the router on the other side, we put it back on because we've made a copy of it. Now, we do have about 2 bytes of header that identifies what voice conversation this is a part of. We don't want to get confused. That's going to be 2 bytes in size, or we could use a UDP checksum, and that would make it 4 bytes in size. But typically, when we do RTP header compression, we're going to have a 2-byte header instead of a 40-byte header. By the way, Cisco says that this is appropriate when the link speed is less than 2 megabits per second. So fairly slow WAN link speed, less than 2 megabits per second. The other link efficiency tool I want you to know about is called link fragmentation and interleaving, or LFI. That's the reason I've got the tractor trailer on screen. Now, this tractor trailer looks like it might have a couple of trailers behind it, but there are some tractor trailers out there that have 3 trailers behind the tractor in front. And imagine that you're in your little tiny sports car and you're behind one of these big triple tractor trailers and you're at a traffic light. And the light turns green, and slowly the tractor trailers start to go through the intersection. The first trailer goes through, and the second, and then finally the third. By the time you get to the intersection, the light's probably red again. That's a lot like our voice traffic getting trapped behind a big data packet. For example, if we had a 1500 byte data packet trying to go out of an interface, just to give you an extreme example, if we had a really slow WAN link, let's say 56 kilobits per second, just because of easy math, it would take 214 milliseconds just for that data packet to get out of the interface. And that would adversely delay the voice traffic, and it would give us poor voice quality because we've got too much delay. What we can do instead is take that big data packet and break it up. Going back to our tractor trailer metaphor, instead of having one tractor with 3 trailers behind it, what if we put a tractor in front of each of the trailers? Now we've got 3 separate vehicles on the road. We've got 3 separate tractor trailer combinations. And in our little tiny sports car, we're nimble, we're agile. We could probably weave in and out and get ahead of 1 or 2 of those tractor trailers. That's what we can do with link fragmentation and interleaving. We can take that big data packet and bust it up into little tiny fragments. And then, just like we're shuffling a deck of cards, we could shuffle in the little tiny voice packets in amongst the now fragmented data packets. And as a result, our voice packets get through the interface sooner. Now, where does Cisco say that we should use link fragmentation and interleaving? It's when we have voice or video traffic on a link speed of 768K or less. That's pretty slow. You probably aren't going to run into too many of those. But if you do, and if you're running voice or video, it might benefit you to consider using link fragmentation and interleaving. If you use link fragmentation and interleaving on higher speeds, it starts to hurt you more than help you. Because if you think about it, when we fragmented that big data packet, we had to put a header on each of those fragments. We now have more headers than we did before. We're actually using more bandwidth than we did before. But it's a valuable trade-off if we're on a lower link speed and we can get voice packets ahead of some of the traffic, but it starts to hurt us more than help us if we're above 768 kilobits per second. And that's a look at some of the common quality of service mechanisms we have. In this video, we're going to take a look at how we can configure and apply a quality of service policy to a Cisco router. And the way we typically configure quality of service is using a 3-step process. This is called the MQC process for Modular Quality of Service Command Line Interface. So MQC. The 3-step process begins with the first step, which is the creation of class maps. You might remember from a prior video, we discussed how Cisco recommended that we create no more than 11 different categories of traffic in which to place our traffic. Well, those categories are created with class maps. And let's create a few of them here. Let's go into global configuration mode with the configure terminal. And let's create a class map that's going to match email traffic. Now, with email traffic, we have different protocols that will be categorized as email. We've got POP3 and SMTP and IMAP and Microsoft Exchange. I want to be able to match any of those. So I'm going to have multiple criteria within this class map to say match any of those. And it's important to know if you're trying to match on more than one characteristic, there's some Boolean logic at work here. Let me show you what I mean with some context-sensitive help. We can do either a match all or match any. And here's a huge point. The default is match all, meaning that if I say match POP3, match SMTP, and so on, in order for a packet to be categorized in this class map, it would have to match all of those criteria. And that's not possible. We cannot have a packet simultaneously be a POP3 packet and an SMTP packet. What I need to do in a case like this is to use the other logic of match any. If I match any single criterion, then the traffic is going to be placed in this class map. So I'm going to say class-map match-any, and I'm going to give my class map a name of, I'll just say email. And you don't have to make it uppercase. I think that's a best practice to make things that you create, things that you're giving a name to within Cisco iOS. I think it's a good practice to make those uppercase. That way, when you're looking through the configuration, you're going to be able to see something in all uppercase, and you're going to say, oh yeah, that's something that I created. That's not some sort of a Cisco iOS keyword. Now, notice I'm in class map configuration mode, and there are lots of ways that I can match traffic. I could match based on existing quality of service markings. I could match based on the ingress interface, just so many things. But here's my favorite though, it's match protocol. And if we give some context-sensitive help here, you'll see that Cisco iOS automatically knows how to recognize a plethora of protocols, including all the different email types that we're looking for. So what I'm going to do is say match protocol, and I'll follow that with POP3, and I'll give the command again. This time I'll follow it with SMTP, then we'll do IMAP, then finally we'll do Exchange. And we've created our first class map. And let's exit out of that class map configuration mode. Let's create another class map for voice traffic if we want to give it high priority treatment. We talked about the low latency queuing approach where we could put voice and maybe video traffic in a priority queue that gets to go first. Well, let's recognize that voice traffic. I'm going to say class-map, and I'm going to recognize voice traffic, so I'll call the class map voice. Now notice, I did not say match any or match all. And that's because I'm only going to give one match statement. There's nothing to compare it against. So the Boolean logic really doesn't matter in a case like this where I just have a single match statement. And I'm going to say I want to match the protocol of RTP. Remember we talked in a previous video about the real-time transport protocol that carries the voice and also the video media. And we could stop right there, but this match statement would actually match voice and video. If I wanted to just get voice, I could be specific and say RTP audio. Now let's exit from that class map configuration mode and create another class map. I'll say class-map, and this will be for our more undesirable traffic. I'll call it our scavenger traffic. And let's say that we want to recognize maybe BitTorrent traffic. And yes, I know that a lot of companies use BitTorrent for very legitimate file transfer purposes, but come on, some people don't use it for those purposes. So let's say that in our particular business model, we don't want BitTorrent, or we want to limit it anyway. I'm going to say I want to match the protocol of BitTorrent. And we'll say that that's enough class maps for now. That was step 1 of MQC, the creation of class maps. Let's go on to step 2, which is the creation of a policy map. In a policy map, we're going to go into policy map class configuration mode for the different classes we created, and we're going to say what kind of policy we want to apply. So let's create a policy-map statement, and we'll call the policy map demo. And if I give context-sensitive help, you'll see not much happens within policy map configuration mode. The real magic happens within policy map class configuration mode. I'm going to say class followed by one of the class map names that we just created. Let's start with email. And notice we're now in PMAP-C, that's policy map class configuration mode. And this is where we apply most of our quality of service policies. This is where I can turn on policing or shaping, I can do marking, I could do class-based weighted fair queuing or low latency queuing. Just about everything can be done quality of service-wise in this configuration mode. And for the email traffic, I don't want it to be priority traffic, but I want to give it a certain bandwidth guarantee during times of congestion. And let's say that I decide on 512 kilobits per second. I'll say bandwidth 512. Now what that means is during times of congestion, I guarantee that this traffic is going to have at least 512 kilobits per second of bandwidth available to it if it needs that much. And more if it needs more, and more is available. Now, let me say that again. I worked really hard on getting the wording very specific there. I'm saying with this command that we want to guarantee that even during times of congestion, that this class of traffic can have at least 512 kilobits per second. A lot of people think when I type that command in, I'm limiting us to 512 kilobits per second. That's not the case. This is my minimum bandwidth guarantee. But I said I'm going to guarantee that we can have at least that much if we need it. If we don't need it, we can let somebody else use it. Remember, this is not the strict QoS model. This is the less strict model. This is the diff-serve model. So if we don't need bandwidth for this class map right now, we can let somebody else have it that might need it. So we're going to guarantee at least this much bandwidth if it needs it, and more if it needs more, and more is available. And now that I've turned on class-based weighted fair queuing for this class, I can then optionally turn on weighted random early detection. And I say I can now turn it on because before you can configure weighted red for a class like this, you first have to either configure class-based weighted fair queuing or shaping. And I've configured class-based weighted fair queuing, so now I can, if I want to, configure weighted red. And to do that, I'll say random-detect. And if I pressed enter right there, that would turn on weighted random early detection. And we talked about the different thresholds that we have with weighted red. We're going to say for a particular priority marking, there's a minimum threshold. Let's say it's 20 packets for a particular marking. And until the queue depth gets to 20 packets, then we're not going to be dropping any of those packets marked with that priority value. But once we exceed 20 packets in the queue, then we're going to introduce the possibility of discard. And that probability that we're going to discard a packet is going to increase and increase and increase until we get to a maximum threshold. And if we surpass that maximum threshold, there's a 100% probability of discard for that marking. Now, just by saying random-detect and pressing enter, it will do what I just described, but it will do it for the older IP precedence markings that use only 3 bits for a marking, not our DSCP markings, which use 6 bits, which is probably what we're going to be using today. So it's important that we, in most cases, say DSCP-based. That's going to apply default minimum and maximum thresholds to specific DSCP markings. Let's now configure our voice class. We'll say class space voice, and I do want this to go first. I want to give it priority treatment. I'm going to say priority 256. And what that says is traffic in this class gets to go first, and it can use as much as 256 kilobits per second of bandwidth, but no more. So unlike class-based weighted fair queuing, where we said we can have more if we need more and more is available, we don't want our priority traffic to potentially starve out anybody else. So not only are we saying, yeah, you can have as much as 256K, we're saying you can have no more than that because we don't want you to starve anybody else out. And here I'm putting voice traffic in a priority queue. What if I had another class map? We didn't create it, but what if I had another class map for video? For video, I could say priority 512 perhaps. What would that do? Would that put it in a different priority queue? No, here's another huge point. There is one and only one priority queue. And if we put both voice and video into a priority queue, they're sharing the same one and only priority queue that we have. All right, let's go into our scavenger traffic now, the traffic that we're not particularly fond of. I'll say class scavenger. And here I want to set a speed limit on how much bandwidth we can use. And I can do that with policing or shaping. Cisco recommends we use policing on higher speed interfaces, and I'm going to be applying this to a gig interface, so I'll use policing. And we'll say police, and there's lots of options that we can play with here, but just the default behavior is this. The units of measure are in bits per second, by the way, not in kilobits per second. I'm going to say police 128,000 bits per second, so 128 kilobits per second. And just by pressing enter without giving any other parameters, here's what that does by default. It says that traffic in the scavenger class that tries to exceed 128K, it's going to be dropped. Traffic that does not try to exceed 128K, it's going to be allowed. And that's the creation of policies for the class maps we created. By the way, there is another class map I didn't tell you about. By default, we've got another class map called class-default. It's there by default. We didn't create it. We cannot delete it. Think of it as the catch-all class map. If we don't specify traffic to go into one of our class maps, then by definition, it's going to go into the class-default class map. So when Cisco says don't create any more than 11 classes of traffic, we could still have 12 classes of traffic. The 11 that we create plus the class-default that's there by default. And a best practice recommendation for that class-default class map is to turn on something called weighted fair queuing. Now that's an older queuing mechanism, but it tries to make sure that no one data flow takes over and dominates the available bandwidth. So it's generally good practice to turn that on within this class that we didn't even create. And we can go into that class map by saying class-default. And I'm going to say fair-q. That turns on weighted fair queuing. We've now done step 2 of MQC where we've created our policy. Now let's apply our policy. Let's go into interface gigabit 0/2, and we typically apply a policy to an interface. And the way we do that is say service-policy, and we can say, are we applying this as traffic is coming into this interface or as traffic is leaving the interface? And it's important to note that some of our quality of service mechanisms don't work in either direction. For example, I've configured class-based weighted fair queuing, and that's only going to work in the outbound direction. So I'm going to say service-policy output, and the name of my policy was demo. And we're done. Now, to verify this, there are different verification commands. You can do a show class-map, a show policy-map, but my very favorite and probably the most powerful command to do our verification is show policy-map interface, followed by the interface identifier of where we apply the policy. We'll say 0/2. And notice the output that we get. It tells us the different classes we created. It tells us how we categorize traffic into those different classes by matching POP3 or SMTP or so on. And we can see if we have any traffic. Now here in this demo network, I don't have traffic passing through this interface, but if we did, we would be able to see actual packet and byte counts to indicate that traffic really is being queued into these different queues. And that's a look at the three-step MQC process for quality of service configuration. Let's take a look in this video at how we can do quality of service in a wireless LAN environment. Wireless LANs often support a feature called WMM, or Wi-Fi Multimedia. And what WMM does is it gives us 4 different categories for accessing the wireless network. It gives us 4 access categories, and here are their names. We have one for the background traffic, that's low priority. Best effort, just sort of average priority. We've got a class or a category for video and a category for voice, and on screen you see the different names given to those different categories. And how we put traffic in the categories is we take a .1p marking from a client, and we put it in one of the categories based on that .1p marking. Now, an 802.1p marking is supported by some network clients, and what we're doing is we're adding 4 bytes onto our frames. It's a lot like adding 4 bytes on a .1q trunk. In fact, it looks almost identical to that. The big difference is the VLAN field is all zeros. We're not identifying VLAN membership. We're just adding those 4 bytes so that we can use 3 bits in those bytes to identify the priority of a frame. So we've got 3 bits at our disposal. How many possible values is that? It's 8. 2 raised to the 3rd power is 8. So we've got values in the range of 0 through 7. And on screen you see how the .1p markings in the range of 0 through 7 map to these different access categories. Now, if we're in one category versus another, what exactly does that mean? Well, your category membership influences interframe space and the random backoff timer that you're going to be using. Here's what I mean. When we're sending frames out in a wireless network, there is a gap that we have between those frames. That's called the IFS, the interframe space. Well, for higher priority traffic, for example, the voice, the video categories, we start to use smaller and smaller interframe spaces, so we're sending more aggressively. Also, wireless networks can use CSMA-CA, carrier sense multiple access with collision avoidance. What that's going to do is it's going to listen to the airwaves to see if it's free to send right now. Now, this is prior to Wi-Fi 6. With Wi-Fi 6 or 802.11ax, we start to move away from this a little bit, and we're given time slots in which we can send, so we don't have this contention issue. But traditional wireless LANs would listen to the airwaves to see if it's free to send right now, and if it is, they'll send. If not, they'll wait a random amount of time and they'll try again. Well, that random amount of time gets smaller and smaller as we increase our priorities, as we go up in the stack that you see on screen. Again, the idea is the higher the access category, the more aggressively we're trying to send our traffic. And that's the way that we can take a .1p marking on a network client and translate that into how aggressively we're going to be trying to send it on the wireless network. Now let's go out to a Cisco wireless LAN controller and take a look at how we could assign one of these WMM categories perhaps to an entire wireless LAN. What we can do with the Cisco wireless LAN controller, and we're sitting at the management screen of one of those controllers here, what we can do is assign different wireless LANs for different traffic types. We might put video in one wireless LAN, voice in another, and so on. And for the wireless LAN that I have, let's go under WLANs, and I've got one called CCNA that I use for my CCNA training. Notice that there's a tab that says QoS. If we go to that tab, we see that we can specify the quality of service for this wireless LAN. And these are the 4 categories we talked about: background, best effort, video, and voice. And right now, this CCNA wireless LAN is just set to best effort. But that's a look at how we could go in and set the access category for a particular wireless LAN on a Cisco LAN controller.
Cisco IOS has several methods which are used for packet switching. The oldest method is called process switching, and as you might have guessed, this involves the switch processor, which is used to inspect every packet. This is also the slowest method, and as we discuss the details a bit more, you'll see why that is. Each time a router receives a packet, that packet is stored in the router's memory. The processor is interrupted in order to process and analyze the packet. The processor is going to check the packet against the internal routing table in order to determine where the packet should be directed. So it's going to examine the next hop destination, and it will determine the outbound switch interface that should be used to deliver the packet. The router can also determine the next hop layer 2 MAC address through a table such as the ARP cache. Using all of this information, the switching process will construct a new layer 2 frame header for every single packet. Then the packet will be sent out through the appropriate outbound interface. If that sounds a bit cumbersome, then you're exactly right, it is. This is considered to be the slowest switching method because it requires the processor to be directly involved with every single packet traversing the switch. It also adds some delay to each packet through this whole process and through the header rewriting that happens for each packet. So for the most part, it's not ideal to use process switching in our modern enterprise networks as our primary method. Process switching is available on every single Cisco switch and router platform by default, although more modern devices will not use process switching as the default method. If you want to debug IP packets, process switching must be enabled for that. These types of packets are always process switched. And other than that, I can't really think of a good reason to completely disable the more modern switching options, such as fast switching or CEF, Cisco Express Forwarding, in favor of process switching. It's just not ideal. There's really no reason on our modern networks to ever rely solely on process switching. It's very processor intensive and it's slow. So for the most part, you're likely never going to use that. If we want to take a closer look at this in action, I've got a really simple topology here. I have two PCs that are connected to each other with a router in between those. And both of those PCs have the router set as their default gateway. So in order to see some of this process switched traffic, we can use a debug command and we can enable process switching on the appropriate router interfaces. So let me actually go under both of those interfaces. Under global configuration mode, I'll say interface range, gig 0/1 and 0/2. Under there, I'll use the command no IP route -cache. This is going to disable the faster switching methods, which are going to use the route cache, and it's going to rely solely on process switching. If we go back to exec mode here and we say debug IP packet detail, this is going to enable packet debugging when we do those ICMP pings. Process switched packets are going to show up here in the debug output, whereas if they were fast switched or CEF switched, they would not. Let me jump over to the PC here, and on this particular PC, PC1, I'm going to ping the other host at 10.1.2.5. So I'm going to ping over to PC2. That's the IP address of that. That traffic is going to cross our router. I'll jump back over to router 1, and if we take a look at that, you can see the debug output from those ICMP pings, and I'll point out this particular section where it says routed via RIB, the routing information base. This is otherwise known as the routing table of the router. So these particular packets have been process switched. That's what this tells us. So that's an overview of the older process switching standard that has largely been replaced by faster, more modern iterations. The modern and most preferred Cisco IOS switching process that's in use on iOS equipment is called Cisco Express Forwarding, or CEF. Most of our modern iOS devices use Ceph as the default method. Ceph stores information in a route cache for optimized lookup and more efficient packet handling. Some of the benefits of Ceph include improved performance. This is much less CPU intensive than older methods, meaning that more processing power can be dedicated to other Layer 3 services, things like encryption and quality of service. Also, there's more scalability through a mode called distributed Ceph or DCEPH. When distributed Ceph is enabled, each line card maintains an identical copy of the routing table, and the line card is simply the hardware module that provides the network interfaces. Allowing the line card to handle forwarding themselves relieves the load on the main processor. Ceph introduces two new mechanisms, the Ceph Forwarding Information Base or FIB and the Ceph Adjacency Table. The forwarding information base is conceptually similar to a routing table in that it maintains an identical copy of the packet forwarding information that would be found in the IP routing table. Each time the routing table is updated with new information, the FIB is also updated. So very simply, the FIB contains lists of all of the known next hop destinations. By using the FIB, it's not necessary to involve the processor for route lookup information. The FIB is also a much more efficient lookup structure, able to look up routes much more quickly than using the routing table. The adjacency table very simply contains information about directly connected devices. Any device that can be reached with a single hop across a link layer is considered to be an adjacency, and its layer 2 next hop address would be maintained in the adjacency table. Here we're connected to a router, and if I want to view the forwarding information base that's used by Cisco Ceph on this router, I can use the command show IP Ceph. I've got a fairly simple topology here, but there are some things I'd like to point out. We can see that listed is the next hop address, as well as the associated outgoing interface that's going to be used for that next hop address. We also see that some of these networks are listed as being attached. For example, the 10.1.1.0/24 network, that's listed as attached. This means that the 10.1.1.0 network, in this case, is directly attached to the gig 0/1 interface. We see that's listed as the outgoing interface. Also note the next hop assignment receive. Some of these are listed as receive. For example, 198.51.100.1/32. So this is a specific IP address because we see a 32-bit mask, and this is an IP address on one of the router's interfaces, specifically on gig 0/2. So traffic destined for the router itself at this IP address is going to use this interface, and it's going to be identified with that receive label. Let me break out of this command output, and if we want to see the adjacency table, we can say show adjacency, and I'll say detail to do that. Now this is going to contain information about how to reach a specific adjacency or a specific device that's directly connected to the router. And here you can see some of those specific networks that are reachable by going out of a particular interface. We see the 198.51.100.2. We see .6. And up here we see 10.1.1.2. So we see all of those listed. And underneath the interface listing, we see those are on gig 1, 2, and 3. And so these are all of our adjacencies that are found on this specific device. One more thing to mention when using Ceph is something called punting. So if a packet can't be processed by Ceph for some reason, it is punted to the next fastest switching method. And that preferred order in iOS would first be distributed Ceph that we mentioned earlier, then normal Ceph, and then fast switching, and finally process switching is the last resort. Now, some of the things that might cause a punt condition would include maybe the Ceph lookup process fails. Maybe it can't find a valid entry in the forwarding information base. Or maybe there's a particular layer 2 encapsulation that's not supported by Ceph. And also, very commonly, you'll see fragmented packets in a network. Those are always going to be processed by the router, so they'll be punted down to the process switching mechanism. And those are just to name a few instances where we would see punting happen. So that's an overview of Cisco Express Forwarding and how Ceph uses forwarding information bases and adjacency tables to more efficiently control our traffic. Cisco Catalyst switches use several different types of tables to assist in the switching process. Two of these specialized memory architectures that we're going to compare are the CAM and TCAM. CAM stands for Content Addressable Memory, and all models of Catalyst switches use a CAM table for Layer 2 switching. As data frames arrive on a switch port, the switch will learn the source MAC addresses correlating to that traffic, and it's going to record those MAC addresses in the CAM table. This is done so that next time there's a frame destined for a specific MAC address, the switch knows exactly how to deliver that and the switch port that it should use to do so. The entry recorded into the CAM table includes the port number, the frame arrived on, and the source MAC address associated with the frame, and also the timestamp for the frame's arrival. CAM tables are large, but they are finite. So on a large network, it's completely possible to run out of CAM table space. That's the reason that the timestamps are recorded. In order to manage what are referred to as stale entries, or addresses that have not been heard from in quite some time, the CAM table entries are automatically removed after a particular aging time. And by default, any CAM table entries that are idle for more than 300 seconds will be deleted. Now, this can be changed very simply from global configuration mode on a switch with the command MAC address-table aging-time followed by the number of seconds that you want to set the aging timer to. If a MAC address learned on one switch port suddenly appears on a different switch port. Maybe someone's plugged their laptop into another cubicle in the office, as an example. The port, the MAC address, and the timestamp are going to be recorded for this most recent occurrence, and the old entry will be deleted immediately. That purge happens in order to avoid having duplicate CAM table entries. Otherwise, the switch may be confused when it makes switching decisions. Now, as we've already said, the CAM table can learn those addresses dynamically from incoming frames, which is the default action, but you can also configure static CAM table entries as well. During CAM table lookup, the table will provide one of two results, either a true or a false. So either a MAC address will be found in the CAM table or it will not. Those are the only two possibilities with CAM tables. In binary, this will either be a 0 or a 1 value. So it's going to look for an exact key consisting of binary numbers during the table lookup process. Another memory table used by switches is the TCAM, the ternary content addressable memory. Some layer 2 switches will contain a TCAM for quality of service usage, but primarily we see TCAM in multi-layer switches which have layer 3 capabilities. If you think about traditional layer 3 routing, one of the ways that we control traffic is through the use of access control lists, or ACLs. These ACLs will contain entries that will either permit or deny traffic based on certain rules that we determine. So for example, maybe we have an ACL denying traffic from a specific IP address. When traffic arrives from that IP address, this traffic would be evaluated against the access control list, and if a matching statement is found, the traffic would be dropped. So we can think of an access list as a very common function that uses TCAM. So it uses those ternary content addressable memory tables in the exact same way that we're talking about here. And they do that in order to perform packet matching using wildcard values. The TCAM is essentially an extension of the CAM, but where the CAM can only return two results, either a true or a false, a match or no match found, in other words, the TCAM also has a third state called the any value or the do not care value. So during lookup, this leaves three values: 0, 1, and X. X is the do not care value. These three values are where the table gets its name, as the term ternary is defined as a mathematical value based in 3. So instead of performing exact match searches, the TCAM can perform a broader search based on pattern matching and wildcards. The entries in the TCAM have a particular format referred to as VMR, value, mask, and result. The value refers to the pattern that is being matched, which can include IP addresses, protocol ports, and so on. The mask refers to the mask bits associated with the pattern. So with ACLs, we assign a wildcard mask to our entries. These types of masks are used in TCAM lookups in order to determine which bits are of interest to us. And the result are numeric values that represent the action which should be taken after TCAM lookup. Those can include permit, deny, QoS policing, next hop forwarding, and so on. If we connect to a live interface and we run the command show MAC address -table, this is going to display the contents of our CAM table. Here we can see the MAC address, we can see whether that was dynamically learned or statically learned, and we can see the VLAN number as well, and we can see the ports that those are connected to. We can also specify that for a particular VLAN or interface if we want to by just appending those keywords to the command. We can see the size of the CAM table by using the command show MAC address -table count. And that's going to show the number of dynamic and static addresses that have learned and the total number of MAC addresses that have been learned. You can also see the total MAC address space available, which is pretty huge. We have a lot of those available for us. So these are going to show the MAC address totals for each active VLAN. In this case, I only have a single VLAN on this lab topology, so it's only showing those for VLAN 1. This command output is going to give you a really good idea about the size of the CAM table and even the number of hosts on the network. If we want to view information about the TCAM, now I can't do this with Cisco Viral. That's not supported at this time. But if we wanted to do that, if we had a layer 3 capable device that could do that, we could say show platform TCAM utilization. That's the command we could use, and that would show us the overall utilization for that TCAM. So that's a look at the difference in the CAM and the TCAM. Again, to reiterate, all layer 2 Cisco Catalyst switches use the CAM, while the TCAM is typically seen in multi-layer switches and routers. We do see that in some layer 2 switches for use with QoS enforcement, but by and large, whether the switch is a layer 2 or a multi-layer device will usually determine which type of table is available on the device. We've made mention previously of the fib and rib structures, and we want to outline those a bit more clearly in this video. These structures within an IP network perform two distinct functions. Let's take a closer look, starting with the fib, the forwarding information base. The fib is also sometimes referred to as the CEF table or the IP forwarding table, and this is used to make IP destination prefix-based switching decisions. The fib contains the interface number and next hop information for each reachable destination network prefix. The fib, as we've mentioned in regard to Cisco Express forwarding, is also used in conjunction with CEF. The fib itself is a direct copy of the routing table. Each time a routing change occurs and the routing table is updated, the fib is also updated to reflect those changes. With CEF, the fib is used to make IP destination-based switching decisions, which takes the CPU out of the equation and creates a faster, more lightweight switching process. One of the things to note about the fib is that, generally speaking, the number of entries found within the fib may influence the ability of the router to forward traffic quickly. The more entries there are within the fib, the longer it could take for route lookup to happen. But these days, that isn't much of an issue with our modern equipment. We have very fast ASIC-based forwarding that is nearly equal to line speeds. On Cisco routers that have the ability to use distributed CEF or DCEF, a copy of the fib would be applied to each of the line card modules. This again is another way that the CPU is offloaded in order to increase the amount of traffic that the device can handle without affecting performance. The RIB, or routing information base, is the location where all information related to IP routing is stored. This is not specific to any particular routing protocol, but rather it's used by all protocols, such as OSPF and BGP. Anytime a routing protocol learns about a new route, that route is inserted into the RIB. When a previously learned route becomes unreachable, this route is first marked as unusable and will eventually be removed completely from the rib if the route remains down. And the amount of time that it takes for that to happen, that's dependent upon the routing protocol that's in use and the particular timers that are related to the protocol from which the route was learned. Within the rib, we'll find all routes that have been learned dynamically through protocols such as OSPF, and we'll also see directly attached networks and any manually configured static routes as well. An important distinction is that the rib is not used for traffic forwarding, and it is not advertised to the rest of the networks that are attached to the router. In order to more clearly outline the difference between these structures, let's take a look at this overview. We know that routers have various ways in which they can learn about the best paths towards specific destinations. That can include directly connected devices, statically configured routes, and of course, routes learned through dynamic routing protocols. And here at the top of this overview, we see routes learned dynamically being represented. Each routing protocol has its own internal structure used for routing. So where we see BGP, EIGRP, and OSPF in this example, we can see those respective structures. The BGP table, the EIGRP topology table, and the OSPF link state database. Each of these routing protocols leverages and updates their own structures based on updates that they exchange with neighboring devices, and they do that in order to build a picture of the network. Each one has their own way to determine the best route for traffic based on their route selection algorithms. This happens in different ways depending on the protocol itself, but in each case, the results are inserted into the routing information base, the RIB, and those are based on administrative distance for the route. So for example, if a route is learned via OSPF and BGP, OSPF will be the preferred route because it has a lower administrative distance than internal BGP. Now, you may be wondering, why don't we use this information for packet forwarding? Why don't we use the RIB for that? It seems to have everything we need. And the problem is, some of the entries contained within the RIB may have next hop addresses that are not directly connected. For example, this is really commonly seen with BGP or with statically configured routes. And this is where the forwarding information base comes into play. The FIB contains a copy of the routes found within the RIB. This information is used to resolve next hop addressing, since the FIB has knowledge of the layer 2 data required for forwarding. The FIB will determine which outgoing interfaces are needed for a particular network destination. The completed FIB or CEF table is then capable of making layer 3 switching decisions. As we've already mentioned, any updates happening to the RIB will be copied over to the FIB as well. So that's an overview of the forwarding information base and the routing information base, and how those two structures work together for efficient traffic movement within an IP-based network.